Welcome back. We're talking about section 7 in the Klein's Organic Chemistry textbook, second edition. And section 7 talks about hydrolysis of acetals. And the thing to realize here and remember is that acetals are stable towards base. So if we have a base that tries to react with a molecule, there will be no reaction. But if we do a reaction with hydrogen HCl or H+, we can transform acetals to their corresponding ketones or aldehydes. And this is a useful strategy for deprotection reactions of acetals. So H+ is the catalyst. We use a stoichiometric equivalent of H2O. And so in this case, we would form this ketone and two equivalents of the alcohol. Okay, and so the first thing I want to talk about is hydrolysis of acetals. Hydrolysis means literally hydro is water and lysis means to break. So water is going to break this molecule up back into its constituent starting materials. Now remember that these reactions are in equilibrium, and you can drive this reaction to the right with excess water, or you can drive this reaction to the left with excess alcohol. So pay attention to the reaction conditions and realize that we can make an acetal and then deprotect or remove the acetal. The reaction mechanism here is 20.9. Okay, and let's go ahead and go through the reaction mechanism for the deprotection of the dimethylacetal of acetone. So here we're going to add water and H+, and we're going to form acetone and two equivalents of methanol. So in the first step, we're going to protonate. So again, if you have acid present in your reaction mixture, the first step is always going to be protonation. Okay? So we want to protonate either of those two oxygen atoms. And remember that once we protonate it, now we have a good leaving group. And as always, use the lone pairs of your adjacent heteroatom, nitrogen or oxygen, to kick off the leaving group. We don't want to form carbocations here, okay? So that's an elimination step. And what we form is something that looks a lot like a ketone now, except instead of an H, maybe H+, that's protonated, it's a methyl group, okay? So basically, we're just following the reverse steps of the acetal formation. All right, so that's our first equivalent of methanol. Now on this step, we want to take water, which has lone pairs on the oxygen atom that can engage the carbonyl carbon. Okay, and electrons move up towards that positive charge. So this is another attack step. Okay. And after this, there's going to be a series of proton transfers. We really have to show it stepwise and show every single one of these things occurring. So next, we need to deprotonate. This guy here, okay? So you may remember that that's called the Hemiacetal. So we're halfway there, right? This guy up here is called the Acetal. So now what we need to do is protonate the methyl ether there on the top. This will enable that to be a better leaving group. As always, use the lone pairs that are adjacent to that leaving group in the chapter 20 here. So the lone pairs of the OH group are going to assist with the departure or kicking off of yet one more molecule of methyl alcohol. And I'll draw my ketone upright. You'll notice that there's an OH bond. We can't just remove it and say, oh yeah, we form acetone. we need to show the very last step here, which is a deprotonation step. And we use something in solution. Since there's a vast excess of water, we're going to use water as the weak base to deprotonate that guy there to give acetone. Okay? So it's PEAD, PED. Okay? PED is the mechanism there if you're into memorizing letters. Okay? So protonation, elimination, attack, deprotonation, protonation, elimination, deprotonation. So that's the deprotection of an acetal or hydrolysis of acetals. Okay? The next thing the textbook talks about is the hydrolysis of imines, I believe. I can't really find it there in the book. So we'll talk about it here. I don't remember which mechanism it is, but this is the hydrolysis of imines. Okay, so remember again that an imine has this structure here. Okay, there's 3 bonds to the nitrogen in total. There's a carbon-nitrogen double bond. And if you treat this with water, okay, in an acid catalyst, a large excess of water will drive this equilibrium to the right, and you'll form an aldehyde and a primary amine. Okay, primary amine. So let's go ahead and work through the curved arrow reaction mechanism for this. As I mentioned, the first step in your mechanism is always going to be protonation of the nitrogen. That's always going to be the first step of your reaction mechanism, okay, if you have an acid catalyst present. So we'll go ahead and do that. And you'll notice that this looks a lot like the iminium ion. So basically, we're just reversing the steps of the curved arrow reaction mechanism for the formation of imines. So this first step we can label P for protonation. Now we have a vast excess of water. So here's where water is going to attack the carbonyl carbon. Okay. We have a positive formal charge on that oxygen now. And now here we want to deprotonate using the reaction solvent, which is water. Okay. And there's no shortcut here. All chemistry professors would, require you or request of you to draw each of these individual steps one by one by one. If there was a shorter mechanism, I would, of course, present it. But we have to show all the elementary steps one by one. And here you may recognize that this is what we call the carbonylamine. Okay, carbonylamine is an alcohol and an amine on that same carbon, and we started with an amine here. So we're kind of halfway there. And now what we need to do is we're again interested in kicking off the amine. So we need to protonate this nitrogen here, so we're going to use H+ for that. Now that we've protonated the nitrogen, that makes it a pretty good leaving group. And the OH, or the lone pairs on this hydroxyl group, can assist with the departure of this leaving group. So that's the elimination of the leaving group. And so I'll just write negative or minus or losing CH3NH2. Okay, so that's, that's one of the products. And what we get here, I'll draw the aldehyde right side up here. What we form is a protonated aldehyde. And I'll go ahead and use water. Maybe technically you should use the amine as a base, but I'm just going to show water here as the solvent, that's present, that's going to deprotonate the proton here. And so that's D for deprotonation, and we'll form our neutral aldehyde. Okay, so that's another reaction product. So you form two things, the aldehyde and the primary amine. So let's look at the letters here. We have protonation, attack, deprotonation, and then protonation, eliminate, deprotonation. So that's PADPED for short, okay? Okay. So the last thing I want to talk about, and I don't remember which mechanism it might be in the book. They might even skip it completely. Okay, and then the hydrolysis of enamines is the last thing the book talks about. And again, these guys are stable to base, so if you add acid and water, it will push the equilibrium over to the secondary amine and the ketone or the aldehyde. So let's go ahead and do, whoopsie daisy, let's do a dimethyl guy here. And so if we treat this with water, with an acid catalyst, we'll form acetone and dimethylamine. Okay, so my curved arrow reaction mechanism should show the production of both of these. All right, so first step, we want to protonate this molecule. Now, what we want to do here, it's kind of tricky, is we want to protonate the carbon atom, okay? And that would be taking this reaction in the very exact reverse manner that we form enamines. Okay, so what we form here is an imine type looking thing. Okay, so this is the iminium ion, okay? It's the iminium ion. And next we want to take water, so that's protonation. We want to take water. We want to attack the carbonyl carbon. Okay. The whole goal here is to kick off the nitrogen, okay? Break that carbon-nitrogen bond. And remember that we need to protonate the nitrogen, but the oxygen here is protonated, so that's the wrong thing. So we need to keep taking solvent, which is water, to shuttle the proton back and forth between the different groups. So we remove the proton here from the oxygen atom. And yes, you might recognize this as the carbonylamine. Now what we want to do is protonate the nitrogen here, okay, because that's the ultimate goal here for the leaving group. Again, protonation can occur on every heteroatom again and again and again. All of these steps are in equilibrium, okay? But eventually what funnels down and through the reactive intermediate to give you the final reaction product is the thing I'm drawing now, okay? And what we can do now is to kick off the nitrogen. And I'll draw my carbonyl pointing upwards in the usual fashion. And below the arrow, I'll just say minus CH3 to NH. That's the leaving group. That's that product there. And you can see here we're almost to acetone. We just need to deprotonate it. And yes, it would be strictly best to use the amine for deprotonating. But I'm just going to show the reaction solvent here, deprotonating that proton there, okay? And that's going to give acetone as my second product, okay? So let's see, I have protonation, attack, deprotonation, protonation, elimination, deprotonation. So that's PADPED, okay? So for the enamine, it's PADPED. For the imine, it's PADPED. And for the hydrolysis of acetals, it's PEDPED. You have that extra addition step in there, okay? Yeah, you have that elimination step there, okay? So anyways, because you're eliminating two things. So I hope this video helps you. That's all I want to say for section 7. They just want to mention that, look, the hydrolysis does occur. It's in equilibrium, and you can go both ways. Okay? So thanks for watching.